Hi all, welcome back to the rest of Chapter 5. So still dealing with gases, ideal gas law, different variations of those gas laws. So the next topic in Chapter 5 is calculating now the partial pressure of a gas from a sketch. So I first alluded to this pretty early on in the discussion of Chapter 5, where if we have two gases from A and B present in some vessel, and gas A has a certain pressure, gas B has another certain pressure, the total pressure is additive. So this partial pressure of gas A adds this partial pressure of gas B to give us our pressure total. So that's the overall gist of this idea of partial pressures. In this practice problem, dealing with partial pressures, some N2 gas, so dinitrogen or nitrogen gas, is mixed with oxygen gas, and the sketch below shows a representative sample mixture. The total pressure of the mixture is measured to be 0.130. What is that unit again? Well, K is for kilo, so kilopascals. Calculate the mole fraction now and partial pressure of each gas in the mixture based on the sketch. From these colors here, these are oxygen, and then the blue is our nitrogen. So both oxygen and nitrogen are Brinkelhoffs, so they exist as diatomics. So here's oxygen, and then here is nitrogen. So those are going to exist as N2 and O2. So the pressure a gas exerts comes from the constant collisions of gas molecules with the walls of some container. So I first drew something like this too pretty early on in Chapter 5, but that pressure that we observe that a gas is exerting comes from the constant collisions of these gas molecules with the walls of a container. So remember, pressure is really some force over some determined area or some specific area. So whatever force those gas molecules are exerting on the side of a container or a reaction vessel, that force they're exerting, given some area they're exerting that force over, that is our idea of pressure. The more gas molecules there are, the more collisions will happen. Therefore, the more gas molecules, the more collisions, ultimately a higher pressure. So more molecules lead to more collisions with the sides of the container. With more collisions, we think of that as more pressure. More force is being exerted from more gas molecules over some area. So back to partial pressures then. In a mixture of gases composed of gas A and B, in our case, nitrogen gas and oxygen gas, in a mixture of gases, the contribution to the total pressure from each gas, called the partial pressure of that gas, is proportional to the relative number of molecules of that gas. So the total pressure is going to equal the pressure that results from our oxygen gas molecules plus the pressure that results from our nitrogen gas molecules. The more oxygen molecules there are, the more pressure exerted from the oxygen molecules. Then similarly, the more nitrogen molecules there are that are exerting pressure, that's going to increase the pressure that's being exerted by the nitrogen gas molecules specifically. So more oxygen molecules, more partial pressure from the oxygen, more nitrogen molecules, more partial pressure exerted from the nitrogen, leading to an overall more total pressure because these are additive. Partial pressure of oxygen plus partial pressure of nitrogen leads to our total pressure. That is given that oxygen and nitrogen are both present in the same vessel. So with more molecules, more collisions, the higher the pressure exerted. So for example, if half the molecules in a mixture of gases are N2, then half of the total pressure comes from the collisions of N2 molecules. Those N2 molecules, as they're exerting pressure on these sides of the wall, so they're moving about this reaction vessel or this vessel and then colliding with the sides of the wall, exerting pressure. So if we have a mixture of oxygen and nitrogen and we're told that half of the molecules present are from the nitrogen, then for instance, if we knew this pressure was 0.5 atmospheres, the other half of the pressure has to be from oxygen. That also then has to be 0.5 atmospheres. That leads to an overall total pressure of adding these two together. So overall, the total pressure then would be 1 atmosphere. So 0.5 atmospheres from the nitrogen molecules, 0.5 atmospheres from the oxygen molecules. The term partial pressure here is because the total pressure partially comes from the nitrogen that's present and partially comes from the oxygen that's present. So these partial pressures make up the total pressure. Now you may be wondering, well, aren't nitrogen and oxygen somewhat different in their size, their atomic mass, their molecular mass, I should say, because these exist as diatomics, not just as individual molecules, but as diatomics. So we might think that molecules with different mass contribute different amounts to the pressure, since a collision by a heavier molecule might strike a, quote, heavier blow than a collision by a lighter molecule. However, though, while this is a reasonable thought, given what we know, this is not true. This does not turn out to be the case. For ideal gases, the mass of those molecules does not matter. The pressure exerted by one molecule of oxygen will be equivalent to the pressure exerted by one molecule of nitrogen. The relative masses do not matter for the pressure that these molecules will exert, at least for ideal gases, so molecules that make up ideal gases. So one bullet point that is true is that the impulse or the pressure delivered per collision is indeed proportional to this term that does include mass, this mass times velocity term. While there is some proportionality, we're not really going to work much with this mass times velocity term. And with careful analysis, it shows that the typical velocity of a molecule in an ideal gas is proportional to 1 over the square root of the mass. The rate of collisions is also proportional. So this alpha symbol is a proportionality constant, or this symbol means is proportional to. The rate of collisions is also proportional to 1 over the square root of the mass. So it turns out that these two factors, the velocity and then the rate of collision, so how many collisions per second, for example, in these two factors, the mass amount ends up getting canceled out. What does this all mean for us? It means that the takeaway is the result is that the contribution to the pressure from each type of molecule, we're going to get back to our practice problem here in a second, so N2 and O2, the contribution to the pressure from each type of molecule is only proportional to the number of these molecules and not to the mass of the molecule. The relative mass of N2 versus O2 does not matter. The only portion that matters here for our partial pressure kinds of problems is the number of these molecules. So for our practice problem, we're not concerned with the mass of N2 versus O2. We want to look at how many N2 molecules there are and how many O2 molecules there are for this partial pressure practice problem. So going back to look at this image here, remember, we're not going to ask what is the mass of O2 versus N2. We do not need the mass for this problem. What we are going to ask is how many of each molecule there are present. It doesn't matter that it's N2 versus O2, how many are present. So for oxygen, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 O2. For N2, we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 N2 and 12 O2 in our vessel. For these partial pressure problems, we have now how many of N2 and how many of O2. What's also going to be important for these partial pressure problems now, so we have how many. We are going to want to connect how many of A and B or how many of N2 and O2 there are relative to the total number of molecules. The total number of molecules then relates to the total pressure exerted by both A and B. So because of this fact, we should also total this up. So out of our 20 gas molecules, ideal gas molecules, 8 of them are N2, 12 of them are O2. That is the main component we need to solve this partial pressure problem. So from our ideal gas laws, we can connect now that because there are 8 out of 20 molecules of N2 present in our vessel, and we have then 12 out of 20 molecules of O2 out of the total gas molecules present. Because of our ideal gas laws, we can connect this number of molecules to the partial pressure of each. It doesn't matter the identity, right? It's just the fact that there are 8 of 20 are from the N2, 12 of 20 are from the O2. Now we connect this number of molecules to pressure, more specifically to our partial pressures, because 8 of the 20 N2 molecules will have some partial pressure that we denote as the pressure of N2. Similarly, these 12 out of the 20 O2 gas molecules are going to exert a partial pressure that's just from the O2. The partial pressure from N2 relates to there being 8 N2 molecules. The partial pressure from O2 relates to there being 12 O2 molecules. So how we end up thinking about these partial pressure problems is sort of like a weighted average. We are told the total pressure in the mixture is 0.130 kilopascals. So what I mean by weighted average, we know the total pressure, then we know the contribution from nitrogen. That pressure from nitrogen relates to how many nitrogen molecules there are total. Similarly, the partial pressure of O2 connects back to how many of O2 there are. This symbol here is chi. This symbol here is the mole fraction. We already calculated this, we already determined this. I just want to show you this in the proper notation here. And so you can apply this formula to future problems, just replacing N2 and N2 with your other gas molecules present. You also may not always have just 2 present, there could be 3. But in that case, we would add on another mole fraction term and another partial pressure term to get our total pressure. Let me show you this chi N2 then. This is the number of N2 molecules out of the total gas molecules. So we already found chi N2 to be the number of N2 molecules is 8, divided by the total gas molecules is 20. So chi N2, or the mole fraction, is 8 out of 20. Then chi O2 has to be 12 out of 20. What this mole fraction helps us do is it says that 8 out of 20, or 8/20ths of the total pressure, comes from N2. Similarly, 12/20ths of that total pressure is from the O2. In total, they have to add up to this total pressure. The partial pressure from N2 is from the fact that there are 8 out of 20 N2 molecules. So 8/20ths of the total pressure is our pressure from N2. The other portion of that total pressure has to come from O2. That is 12/20ths of this total pressure is from O2. So remember, we're always going to ask how many to figure out the portion of N2 out of the total gas molecules present. How many of O2 then are present out of the total gas molecules? Based on how many are present, that tells us the fraction of this total pressure that's contributed by N2. So 12/20ths of the total pressure is contributed by O2. So the partial pressure of N2 then, we know the total pressure is 0.130 kilopascals. From that total pressure, 8/20ths of it comes from N2. So we write this in here to solve for the partial pressure of N2. That comes out to 0.0520 kilopascals. Then for O2, we know the partial pressure of O2 is going to be the total pressure, then 12/20ths of that total pressure is from the partial pressure of oxygen. This comes out to 0.0780 kilopascals. One check you can do is to total these together, and they better add up to our total pressure, because we're not going to get pressure from anything else. The total pressure comes from the pressure of nitrogen and the pressure of oxygen. So the partial pressure then of nitrogen, whatever pressure the nitrogen molecules contribute to the overall pressure, is 0.0520 kilopascals. Then for oxygen, it's 12/20ths of that total pressure. So the partial pressure of oxygen is 0.0780 kilopascals. So 8/20ths of the total pressure, 12/20ths of the total pressure. Now I introduced this concept of mole fraction here on this last slide. The mole fraction is equal to the relative proportions of the molecules, right? For nitrogen, the mole fraction was 8 out of 20. There are 8 N2 molecules out of the 20 gas molecules total. So for chi of N2, we're going to take N sub I over N, where N sub I is defined as the moles or the molecules, because we can somewhat use those interchangeably because they're the same number of molecules for every 1 mole of anything. So the moles of nitrogen, or the molecules of nitrogen, there were 8 out of N, where N represents the total number of moles or molecules of gas in that vessel. This math here also shows why we can use molecules and moles interchangeably. If we wanted to convert molecules into moles, somewhat of a review from earlier on in the semester, there are 6.022 times 10 to the 23rd molecules, atoms, ions, whatever it is. Here we're talking about molecules in 1 mole. This number is Avogadro's number. So if we were going to convert molecules into moles, we would need to incorporate Avogadro's number each time. Those end up canceling out. So then we can look at the molecules of N2 and the molecules of O2 and connect that to our moles of each. We would end up dividing by Avogadro's number in both cases to go from molecules to moles. So if we're doing that in both cases, it gets canceled out. Therefore, when we count up the number of molecules of N2 and O2, we can think of that as the number of moles of N2 and O2. So for chi of O2, total number of molecules, now we can say as total number of moles, given that we understand this conversion factor between molecules and moles using Avogadro's number. Then N sub I for oxygen would be 12, and total is 20. So chi O2, or the mole fraction of O2, chi N2, or the mole fraction of N2 is how we say those. In our problem, we did calculate those partial pressures. That was the 8 over 20 times the total pressure, and the 12 over 20 times the total pressure. Now for the mole fraction, we can report it in a fraction form typically, so 8 out of 20 and 12 out of 20. You can also do a division and get this into a decimal form. These are also not simplified fractions, so both these are divisible by 4, but we can take 8 divided by 20 and get a decimal form of the number, take 12 divided by 20 to also get a decimal form of the number. So decimal form of the number, decimal form of the number, partial pressure of N2, partial pressure of O2. As a check for our mole fraction, that always has to total up to 1 total. 1 total represents everything that's in that gas vessel. So there is 0.4 contributed from N2, 0.6 contributed by O2. That has to total up to 1. Then these partial pressures of N2 and O2 respectively also have to add up to the pressure total we were given in the problem. Then this note here, for future reference, it's useful to keep in mind that mole fraction is the same idea, and it's numerically equal to the relative proportion of atoms or molecules in a mixture. For example, a mole fraction of 0.5, just means that 50% of the molecules in a mixture have that mole fraction of 0.5. A mole fraction of 0.25 means 25% of the molecules in a mixture, and so on. So these mole fractions are really handy. It can tell us how many molecules, how many atoms, how many ions of A there are in total from this idea of a mole fraction. Because we know we use Avogadro's number to go between moles and atoms, or moles and number of molecules, or moles and number of particles. So using Avogadro's number, we can think of a mole fraction in all these different ways. So the next topic now in chapter 5, similar, so calculating partial pressure in a gas mixture. We talked about Boyle, Charles, Avogadro, Gay-Lussac, so all their contributions to these ideal gases and gas laws. To give credit where credit's due for this idea of partial pressures, this came from the scientist Dalton. So Dalton's law of partial pressures is the formal name for this idea. So we've looked at this idea now. So pressure total is the contribution from the pressure of gas 1 and the partial pressure, so the contribution from gas 2. You take the partial pressure of gas 1 plus the partial pressure of gas 2. That gives us pressure total. This is the law of partial pressures, that these individual partial pressures are additive to find our total pressure. If nothing else is changing, so volume and temperature are constant, then this Dalton's law of partial pressure holds. If we are changing the volume or we are changing the temperature, again, that introduces another added variable here in our ideal gas law or within our laws that describe ideal gases. So these have to be constant for this to hold true. Typically for the problems we're going to see in this class, these do hold true. These are constant, meaning we can use this equation for Dalton's law of partial pressures. Now, I did mention that there's not always just 2 components. If there are 3 components, then we keep adding on however many components there are, right? So partial pressure 1 plus partial pressure 2 plus the partial pressure of some third gas, that still totals up to our total pressure. So at the same volume and temperature, at constant volume and temperature, the total pressure inside the container will be equal to the sum of the pressures of each gas, or the sum of their partial pressures. Again, this has been mentioned a few times, so just to reiterate, Dalton's law of partial pressures states that at constant temperature and volume, the total pressure of all gases in the container will be the sum of the individual or partial pressures of each gas that's in this container. So we've gone through partial pressure now. For some additional equations related to partial pressure and even connecting partial pressure to our ideal gas law. If we're denoting that the partial pressure of gas A is P sub A, we can connect that to the ideal gas law with the moles of A. So what we're doing here is we're taking the ideal gas law, PV equals nRT, but we're denoting that that pressure term relates to our gas A, and the number of moles is specific to gas A. So this is PA equals N sub A RT over volume. So that's how we would get the ideal gas law, but specifically related to the partial pressure and the number of moles of some specific gas that's within a mixture. Then the pressure of B could be calculated the same way of gas B. This is considering that A and B are in some given set amount of volume. That volume is not changing and the temperature is not changing for this partial pressure, for these partial pressure equations to hold. Now this one we've seen as well, so the total pressure is equal to the partial pressure of gas A plus the partial pressure of gas B. So these are additive. This is the mole fraction of A. We recognize that as the number of moles of A divided by the total number of moles total. If only A and B are present in that mixture, then the total number of moles is N sub A plus N sub B, or the total number of moles of A plus the total number of moles of B. Then this mole fraction for gas B is the same, except we're taking the moles of B divided by the total moles. Total moles of gas, technically, right? But all in chapter 5, we've been working with gases. Then how we solved that previous problem is that the partial pressure of gas A or of nitrogen gas, it's equal to the mole fraction of gas A times the pressure total. Similarly, the partial pressure of gas B is equal to the mole fraction of B times the pressure total. Just to show you this explicitly again, so we took the partial pressure of O2, we calculated that as the pressure total times the mole fraction of oxygen. We did the same thing for nitrogen. So we ended up using these two equations in that previous practice problem. But as we know, there's not just always A and B present in some same volume or in some vessel. So this can apply to any gas. Is it gas A, gas B, gas C? Just generally speaking, for any gas, just denoted as I, the partial pressure of that gas I is equal to the mole fraction of that gas I, so the number of moles of I, amongst the total number of moles of gas times the pressure total. So this is taking these equations and just making them slightly more general. So for any molecule of gas, any identification of gas, just denoted as I. Then to also make this more broad, more general, the mole fraction of I then is the moles of I divided by the total number of moles of gas. So these are all of our equations for Dalton's law of partial pressures. We did that previous practice problem from that image. We're going to do a little more practice on partial pressures now. We have a 9.00 liter tank at 20.2 degrees Celsius filled with this many grams of sulfur hexafluoride. Just remembering how we name molecular compounds, sulfur, then hexa, fluoride, so 6 of them, 6 fluorines, gas, and 14.5 grams of carbon dioxide, carbon dioxide, so 2 oxygens. Remember, we changed that ending to end in IDE. We can assume both gases behave as ideal gases under these conditions. That's an important assumption. Calculate the mole fraction and partial pressure of each gas and the total pressure in the tank. So before we even go into solving this, some things I can write out and would write out for myself. We know the pressure total is going to reflect the pressure of sulfur hexafluoride plus the pressure of CO2. Once we figure out these partial pressures, we can definitely get the total pressure in the tank. As we looked at previously on this slide as well, we can apply the ideal gas law for gas A, gas B, or make it more general and apply the ideal gas law to gas I. So for any general gas I, we have PV equals nRT. We're going to be at constant volume and constant temperature. The pressure of some gas I and the number of moles of that gas I can be calculated. We can combine this information in the ideal gas law. So if we wanted to solve for the partial pressure of that gas I, then that would be equal to the number of moles of I times RT over the volume. We can plug in the meaning for I here. For us, we're going to plug in carbon dioxide, for example. So here we would have the number of moles of carbon dioxide times the gas constant times the temperature divided by the volume, where the temperature and volume remain constant. Well, as we can see from this ideal gas law, we're going to need the number of moles of sulfur hexafluoride and the number of moles of carbon dioxide. In our practice problem, we are given the grams of sulfur hexafluoride and the grams of carbon dioxide. From this, our very first step should be to convert these into moles of each. So with those gram amounts, we need to convert them into moles. To go between grams and moles, we know we need the molar mass. If we go to the periodic table, find the atomic mass for sulfur, then for fluorine, multiply fluorine's atomic mass by 6, we'll get the grams per mole of sulfur hexafluoride. That molar mass comes out to 146.055 grams per mole. To orient this correctly, we should put 146.055 grams per mole. Right, so we cancel out grams and grams. Then we're left with just moles of sulfur hexafluoride. that mole amount comes out to 0.03084 moles of sulfur hexafluoride. Then for carbon dioxide, we look up the mass for carbon. Then for oxygen, multiply that by 2. That molar mass comes out to 44.0095 grams per mole. To orient this correctly, we will put grams in the denominator, moles in the numerator. This mole amount comes out to 0.32947 moles of CO2. So now we took the gram amounts, we have mole amounts. Going back to our ideal gas law, now we have N. We can plug in something for our gas constant R. Do we have a temperature and volume? Let's see. We're told we're working at 9.00 liters and at 20.2 degrees Celsius. We know for these gas law problems, we should take 20.2 degrees Celsius plus 273.15 to get our temperature into Kelvin. Then we can use this volume term in our ideal gas law. Now we do have number of moles. We can plug in a gas constant. We have temperature, but in Kelvin, and we have a volume. Now we can calculate the partial pressure of CO2 and sulfur hexafluoride. So for the partial pressure of sulfur hexafluoride, I usually like to write out the full ideal gas law, then try to isolate what I want to isolate. So PV equals nRT. I have that down. To just isolate pressure, I'm going to take nRT over volume now because I divided both sides by volume. The number of moles to plug in is 0.031084 moles of sulfur hexafluoride. That's our N term. For our gas constant, we have moles, we have Kelvin. We also have a liter term. We were told the tank is 9.00 liters. That leads to us using the gas constant of 0.08206 liters atmospheres per mole Kelvin. I like to plug in the gas constant usually last because it's more complex with its units. So we took care of N, the number of moles, the temperature converted into Kelvin. So 20.2, so degrees Celsius plus 273.15, we get 293.35. With just 4 sig figs, we can plug in 293.4 Kelvin. Then the volume of the tank, we were told, is 9.00 liters. Now we've dealt with volume, temperature, and number of moles. Now let's incorporate that gas constant, so 0.0820574 or 0.08206. This is liters atmospheres per mole Kelvin. So we put per mole Kelvin on the opposite side of this division line to then better visualize that moles, moles, Kelvin, Kelvin, liters, liters. We want to solve for pressure. We're solving for pressure, so it does make sense that we're left with just atmospheres for our unit. Doing this multiplication and this division, we will get that the pressure, the partial pressure of sulfur hexafluoride is 0.08312 atmospheres. Let's do the same thing for the partial pressure of CO2. We know that we have the same volume and the same temperature, the same gas constant. What is different for carbon dioxide is the number of moles. So on this last slide, we took grams into moles. Then we can use that mole amount for CO2, just like we use this mole amount for sulfur hexafluoride. So this many moles times the temperature is still 293.4 Kelvin. We still have our gas constant here, so 0.0820574 liters atmospheres, but per mole Kelvin. That's just our gas constant R. Plugging in the volume term down here in the denominator, 9.00 liters. Just to double check, moles, moles, Kelvin, Kelvin, liters, liters. Then we should get the partial pressure of CO2 now, also in atmospheres. There are more moles of CO2 than there were of sulfur hexafluoride, so it makes sense that this pressure comes out to be larger, so 0.88136 atmospheres for the partial pressure of CO2. Going back up to our problem, just to make sure we're on the right track, we need the mole fraction of each and the partial pressure of each. We just found the partial pressure of each. So we're asked about the total pressure. We know that the pressure of sulfur hexafluoride, the partial pressure of sulfur hexafluoride, plus the partial pressure of carbon dioxide is going to equal our total pressure. That means we take this pressure in atmospheres from sulfur hexafluoride plus this pressure in atmospheres from carbon dioxide, then we get that pressure total in the end. This amount plus this amount comes out to 0.96451. We haven't yet dealt with sig figs, but that is this pressure plus this pressure. We need to round all these pressures into 3 sig figs, so 0.0831, and the 5 bumps this up to 2, so 0.0832 atmospheres. So 0.0832 atmospheres, we got that answer. 3 sig figs here, 0.881, that stays as a 1. We don't round that up, so 0.881 atmospheres. So here's this answer for carbon dioxide. Then for the total pressure in 3 sig figs, 0.96, this bumps up to 5. So 0.965 atmospheres. Notice that when we added these pressures together, we still kept the full amount of sig figs. We want to calculate the pressure total from this number and this number unrounded. We want more sig figs than we need because then this pressure total, we can always round this down to a certain number of sig figs, but we want to use these full values here before rounding that total pressure. What we're left with now is getting the mole fraction, so sulfur hexafluoride. We know that is the moles of sulfur hexafluoride divided by the total moles. From our last calculation, we have this many moles of sulfur hexafluoride, this many moles of carbon dioxide. We should add these together. This number of moles plus this number of moles comes out to 0.360554. We want to keep these values for now, and then we can round off our mole fractions if we need to. So this many moles of sulfur hexafluoride divided by the total number of moles comes out to 0.0862117, etc. We only want 3 sig figs, so this mole fraction for sulfur hexafluoride is 0.0862, right? So that's our mole fraction. We're taking moles divided by moles technically, so this mole fraction has no units. So mole fraction has no units. For sulfur hexafluoride, we just calculated that to check. Yes, that is our mole fraction. Notice again, no units are needed for mole fractions. Now to solve for the carbon dioxide mole fraction, we could technically take 1 minus the mole fraction for sulfur hexafluoride because that has to total up to 1. We could do it this way. We can also go through, I'll show you the full work for it just to see. So again, we could solve it this way, but we could also take moles of carbon dioxide divided by the total number of moles to then also get our mole fraction for carbon dioxide. We do know the mole fraction of carbon dioxide plus the mole fraction of sulfur hexafluoride has to total up to 1. So this many moles divided by the total number of moles, we get 0.91378, etc. To get this just into 3 sig figs, 0.914. So 0.914, that's this mole fraction with 3 sig figs. So 0.914, to double check what we just did with the mole fractions, we should be able to take the mole fraction, again, of sulfur hexafluoride plus the mole fraction of CO2. That should total up to about 1. When we do some rounding, it could be a little less than 1 or a little bit more than 1, just by some small decimal, but that should total up to 1, and it does. I'm getting this to be approximately 0.99999, etc. But yes, this totals up to approximately 1, as it should. There are some additional practice problems on these partial pressures, so 5.14 and 5.15. We're going to go into the final topic in Chapter 5. Before that final topic, I just want to show you one application of these partial pressures. So we can collect a gas over water, then combining information that we know about the pressure of the water, and we knew the total pressure, we can go back and find the pressure of just oxygen within some reaction involving these two solids. So it's tricky to solve for how much oxygen is being produced in a reaction in the lab. But if we collect this gas over water, we know the pressure of the water, we know the total pressure, we can sort of work backwards to find the pressure of oxygen gas. So I'm going to include an animation here just as one application of Dalton's law of partial pressures, so that'll be included at the end. Now the last topic in chapter 5 is understanding how average molecular kinetic energy scales with temperature. So kinetic energy, sometimes denoted as Ke, as the temperature increases for gases or for any substances really, molecules and atoms are moving around more. Kinetic energy is a measure of energy in motion. So as temperature is increasing, the kinetic energy or the movement of molecules, gas molecules, will also increase. So let's see how this applies to a sort of practice problem we can solve. So these concepts play into this kinetic molecular theory of gases. We're not going to go too much into the actual equations, but just knowing the general concepts behind this theory. So a gas is composed of molecules that are separated from each other by distances far greater than their own dimensions. What does this mean? Well, if we have some molecule of O2, it's going to be spread apart much further from another gas molecule of O2. This is relative to this distance or this space that an O2 molecule takes up. So we kind of think of these gas molecules as certain points in a vessel. They have some mass to them, but they're so small, they're so spread apart, that sometimes the volume taken up of these individual gas molecules ends up being essentially negligible. So they possess mass, these gas molecules possess mass, but they have a negligible volume ultimately when we picture them on this kind of scale. The second point here in this theory, gas molecules are in constant motion, so they're always moving around in a vessel. They frequently collide with one another. We also looked at them colliding with these sides of some reaction vessel. These collisions we've talked about, more on these collisions though now, so these collisions among the molecules are perfectly elastic. If you've taken a physics class somewhat recently, you might remember this term of elastic interactions or elastic or inelastic collisions. When two gas molecules collide, the total kinetic energy is conserved. So the kinetic energy of one gas molecule, kinetic energy of another gas molecule, if those collide, they're still going to maintain the same kinetic energy they had before that collision took place. Point number 3, gas molecules exert neither attractive nor repulsive forces on one another. So some gas molecule here in space, it's not going to repel another gas molecule or attract another gas molecule. They're kind of simple points just floating around in space, colliding with one another in these elastic conditions, and they're neither attracting nor repelling other gas molecules away or towards them. Point number 4, the average kinetic energy of the gas molecules is proportional to the temperature of the gas in Kelvin. This is the big point we need here for our practice problem. So any two gases at the same temperature will have the same kinetic energy. The kinetic energy of the gas molecules is proportional to the temperature of the gas. Importantly, this temperature unit in Kelvin. This is what we need to solve our practice problem. So if they're at the same temperature, they're going to have the same kinetic energy. If some gas molecule is at a higher temperature, it'll have a higher kinetic energy. So let's try a practice problem now with this understanding of the connection or proportionality between kinetic energy and the temperature. So as temperature is increasing, kinetic energy is also increasing. So we're going to use this in solving this practice problem. We're going to rank the samples in order of increasing average kinetic energy of the atoms. We are given the amount, we're given the pressure. It's kind of sneaky here because all we really are concerned with is the temperatures. We're going to write 1 next to the sample in which the xenon atoms have the lowest average kinetic energy, then 2, and so on. So lowest kinetic energy with the number 1 up to a higher kinetic energy by denoting 5, because there are 5 different options here. So as mentioned, kinetic energy is energy in action. It's energy in the form of motion. That means we're being asked about the motion of the atoms or molecules in a gas. If we're looking at the motion of molecules or atoms in a gas, we're talking about their kinetic energy. Therefore, we're talking about the kinetic theory of gases. The key idea we need from the kinetic theory is that the average kinetic energy, also sometimes denoted as E sub K or Ke, so average kinetic energy of the atoms or molecules in a gas is proportional to their absolute temperature. What does this absolute mean? It just means that we need to work in an absolute temperature unit, which is our friend Kelvin. So Kelvin is an absolute measure of temperature. This means we can order the gas samples by their average kinetic energy of the atoms in them simply by ordering according to temperature. We only need temperature information from that practice problem to solve it. So for example, if atoms in a sample with the lowest temperature, they're going to have the lowest average kinetic energy. So lowest temperature, lowest average kinetic energy, highest temperature, highest average kinetic energy. In this equation, again, all we really need to connect is the kinetic energy and the temperature. Just so you're aware, this Kb value, it's our Boltzmann constant. So it's just a constant value we can plug in. If we actually wanted to solve for the kinetic energy or the temperature, for us, all we need to do and understand is that as temperature increases, kinetic energy increases. As temperature decreases, kinetic energy decreases. So what we're noticing is that the moles of the gas in the sample and the pressure of the gas have nothing to do with their kinetic energy of the atoms or molecules. Only the temperature matters. So seeing a problem like this, we can almost just cancel out these columns or cross out these columns. We're only focusing on our temperature. -24 is our lowest temperature, so 1 should go here. Then -4 is next, that would be 2. Next is 3, that would be 3. Then 6, 4, then 15, 5. So 15, the highest temperature, the highest kinetic energy. So 3, 4, 1, 5, 2. Again, what we needed for this question is to think about our kinetic molecular theory of gases, which tells us that the kinetic energy of gases and temperature are directly proportional. As one increases, the other increases. As one decreases, the other decreases. So just using temperature values to then tell us how we can rank their average kinetic energy. You do not need to worry about solving a sort of equation like this or plugging things in, just recognizing the connection between kinetic energy and temperature. Now I am going to include that one last animation in chapter 5, so collecting a gas over water. We're at the end of chapter 5. Please let me know if I can help with anything or you have any questions. I hope you're all doing really well, and I will talk to you then next time for chapter 6. I'm also including here some animations that are copyrighted and they are provided by the publisher.
Potassium chlorate, KClO3, decomposes to potassium chloride, KCl, and oxygen gas, O2, when heated. Manganese 4 oxide, MnO2, is added to speed up the reaction. The oxygen gas produced in the reaction can be collected by bubbling it through water and collecting it in a bottle or graduated cylinder. As oxygen gas is generated, the gas bubbles rise to the top and displace water from the cylinder. This method of collecting a gas is based on the assumptions that the gas does not react with water and that it is not appreciably soluble in it. The oxygen gas collected in this manner is not pure because water vapor is also present in the cylinder. The total gas pressure is equal to the sum of the pressures exerted by the oxygen gas and the water vapor. Consequently, we must allow for the pressure of water vapor when we calculate the amount of O2 generated. The partial pressure of O2 equals the total pressure minus the pressure due to water vapor.